Hello and welcome to the day 4 of the AI Advent Calendar. Today we are tackling something that often leaves people scratching their head. That's right, machine learning algorithms. By the end of this video, you will have a clear strategy for picking the right algorithm for your problem and the basic intuition of how these algorithms relate to each other. Whether you are a small business owner trying to predict trend or a student venturing into the world of AI, this video is here to help you. Stop feeling overwhelmed with all the buzzwords and start feeling empowered. Let's dive in. There is a simple strategy for picking the right algorithm for your problem. Today, you will know how to pick the right one for any problem and get a basic intuition of each algorithm and how they relate to each other. Let's start with a simple definition. Machine learning is a branch of an artificial intelligence that develops algorithm capable of learning patterns from the data and generalize it to unseen data. Imagine this: you've just moved to a new city and are trying to find the best coffee shop. Instead of trying every single cafe in town, you notice patterns. Shops with long lines or those that use locally roasted beans will definitely have better coffee. That's machine learning in a nutshell. Spotting patterns to make smarter decisions. Machine learning splits into two major branches: supervised and unsupervised learning. Supervised learning is when we have a data set with number of independent variables, also called features or input variables, and a dependent variable, also called target or an output variable, that is supposed to be predicted. We also have a data set supposedly called a training data set where we know the values of the output variable. They are called labels. We use these labels to train our algorithm and use it later to predict the output variables for a new and unknown data. Think of this as teaching a kid how to recognize fruits. You show them labeled fruits. This is an apple, this is an orange, and ask them to identify the new fruit. Examples of this can also be predicting the price of a house based on the size and bedrooms, or identifying males whether it is ham or a spam based on its content. Unsupervised learning. Here there is no labels. Imagine handing a kid with a basket of mixed fruit and asking them to sort without telling them what is what. The algorithm groups the data based on the similarities, such as sorting an email into clusters like personal, work, or promotional, without explicitly being told. This is all about discovering patterns. Supervised learning itself breaks into two tasks. One, regression, where we predict the continuous number, for example, how many miles a car can drive on a full tank of gas based on the engine size, weight, and the tire type. Classification, where we assign data to categories, also called classes, for instance, deciding if a review is positive or a negative based on the text, or a fun one, identifying whether this picture is a photo of a raccoon or a panda or a bear. Starting with the queen of all machine learning algorithms, linear regression. At its core, supervised learning algorithm attempts to establish a relationship between two variables. Essentially, they try to find a function that maps inputs to outputs. Linear regression does this by trying to determine a linear relationship between the input and the output variable. The goal is to fit a straight line to the data that minimizes the sum of squared differences between the actual data point and the predictions made by the lines. This minimizes the average error and improves the predictive power for unseen data. Imagine you are looking at the data about the weight of packages and their shipping cost. Linear regression might reveal that for every additional kilogram, the shipping cost increases by 5 pounds. This insight allows you to predict the cost for any given weight. You can also make your model more complex by including additional input features. For example, in prediction of shipping cost, you might consider the shipping distance, the type of package, whether it is fragile or non fragile, and the delivery time, express or standard. These extra variables would improve the accuracy of your prediction. It's worth noting that many sophisticated machine learning algorithms, including neural network, are just an extension of this foundational idea of finding patterns in the data and the relationships between them. Let's move on to logistic regression, which is like a cousin of linear regression but designed for classification problem. Instead of predicting a continuous value, logistic regression helps us predict categorical outcomes. Essentially, which group or a class something belongs to. These classes can be based on either numeric or categorical variables. Imagine we are tasked with the prediction whether an email is a spam based on the features like the presence of a certain keyword, a sender's address, or the email's length. Unlike linear regression, Where we are trying to draw a straight line through the data, logistic regression uses a sigmoid function, which outputs the probability between 0 and 1. Here is how it works. The sigmoid function maps input values to the probability. If the output probability is closer to 1, we might classify the email as spam. If it is closer to 0, we might classify it as a non spam. Let's now look at this example. We now want to predict one of the two classes, for example, gender of a person, based on height and weight. So a linear line wouldn't make much sense anymore. Instead of fitting a line to the data, we now fit so-called sigmoid function to the data, which looks like this. The equation will now not tell us about the linear relationship between the variable, but will now conveniently tell us the probability of the data falling in a certain class given a given value of input variable. So, for example, the likelihood of an adult person with a height of 180 centimeters being a man would be 80%. Have you ever wondered how we could predict something based on the things that it was closest to? That's the idea on one of the simplest and the most intuitive algorithm in machine learning, that is k nearest neighbor or KNN. Whether it is classifying images or predicting trends, this algorithm relies on the basic yet powerful concept proximity. It is also called a non-parametric algorithm. The name means that we don't try to fit any equation and thus find any parameters of a model. So no true model fitting is necessary. The idea of KNN is simple, that for any given new data point, we will predict the target to be the average of its nearest neighbors. While this might seem very simple, this is actually a very powerful predictive algorithm, especially when the relationships are more complicated than a simple linear regression. In a classification example, if you are trying to guess the favorite food of a new coworker, you will ask their five closest friends. Their response helps you predict the answer. In regression example, now you are supposed to predict the rent of an apartment. KNN might consider the rent of the three most similar apartment nearby, similar in size, location, and amenities, and take average and get the answer. Simple, right? This makes a ton of intuitive sense. Here you see k is equal to 3. K basically is the number of neighbors it is compared to. You might realize that the number 3 seems a bit arbitrary, and it is. K is called a hyperparameter of the algorithm, and choosing the right k is an art. Choosing a very small number of k, say 1 or 2, will lead to the model predicting your data set very well, but not generalizing well with the unseen data. This is called overfitting. Choosing a large number, say 100, will lead to a worse fit overall. This is called underfitting. The best number is somewhere in between and depends a lot on the problem at hand. Method for finding the right hyperparameter includes cross validation. That is a larger scope. We will not be covering it today. So, why is KNN so widely used? It is because it aligns with our natural intuition. For example, if you are at a party, you are more likely to feel comfortable around the people you already know, or at least those similar to your friends. But KNN isn't perfect. It can struggle at large data sets because it needs to calculate distances with every data point, and that takes time. And of course, the choice of K is critical to getting an accurate prediction. KNN is proof that a simple idea can lead to powerful predictions. Whether you're sorting emails, pricing homes, or even identifying animals, it's all about finding the right neighbor. So the next time you're faced with a machine learning problem, remember sometimes the answer is just next door. Now we'll be exploring something called a support vector machine or SVM. The magic of SVM lies in the ability to find the best line or the decision boundary that separates two classes. But it doesn't stop at separating, it tries to maximize the margin between the two classes. SVM tries to find the line that separates the classes and the largest margin possible. That is maximizing the space between two different classes. This makes the decision boundary generalize well and less sensitive to noise and outliers in the training data. The so-called support vectors are the data points that sits on the edges of the margin. Knowing the support vector is enough to classify new data points, which often makes the algorithm very memory efficient. One of the benefits of SVM is that it is very powerful in high dimensions. That is, if the number of features is large compared to the size of the data. In those high dimensional cases, the decision boundary is called a hyperplane. Whether you are working with two features or hundreds features, SVM scales beautifully. That makes it powerful for complex data sets. But what if your data isn't linearly separable? That's where the kernel functions come in. Kernels are like secret weapons that transforms the data into higher dimensional space, making the complex boundaries possible. For example, say you are trying to classify animals based on the weight and the height, but a straight line doesn't work. A kernel might create a feature like weight divided by height squared, similar to BMI, to make that boundary cleaner. That is called implicit feature engineering. And that's one of the most powerful part of our SVM tricks. SVM supports number of kernels including linear, best for simple data, polynomial creates curved boundaries, RBF, radial basis functions, grade 4 integrate patterns, and sigmoids often used for probabilistic models. Now let's switch gear to another classifier, naive Bayes. While SVM relies on geometry and boundaries, naive Bayes is rooted in probability. It gets its name from Bayes' theorem, which calculates the probability of an outcome based on the prior knowledge. Here's how it works. Imagine you are building a spam filter. You train the algorithm by analyzing a set of spam and non spam email, counting how often certain words appear in each category. For each words like congratulation and win might appear more in spam, while words like meeting or report might be more common in non spam emails. To classify a new mail, naive Bayes multiplies the probability of all its words being in spam or non spam. Whichever category has highest probability wins. Now, why is it called naive? Because it assumes that all words in the email are independent of each other, which isn't true in real life. Context matters. It's still a good approximation for many text based tasks. And because of its simplicity, naive Bayes extremely fast and computationally efficient. Imagine trying to decide on your next vacation spot. You might start with a simple question, beach or mountain, then sunny or snowy, then cabin or a hotel. Congratulations, you've built a decision tree. Today, you will explore how this simple concept powers one of the most foundational algorithms in machine learning. At its core, a decision tree is a series of yes and no questions designated to split data into groups. For example, let's say you are classifying fruits. Start by asking, is it round? If yes, ask whether it is red. If yes, probably it's an apple. If not, it's an orange. This process continues until we reach the final decision, which is represented by the leaf at the end of the tree. Here's another example of decision tree for classifying people into high and low risk category for heart attacks. The goal of the decision tree algorithm is to create a leaf node at the bottom of the tree that is as pure as possible. What this means is instead of randomly splitting the data, we try to find split that leads to the resulting groups or leaves to be as pure as possible, which is to say that as few data points as possible are misclassified. While a single decision tree is easy to understand, it can be oversimplistic. For example, if one question does not split the data well, the whole tree might fail. But what if we use many trees working together? That's where ensemble methods come in. One popular ensemble method is called bagging, where we train multiple decision trees on different subsets of the data. A famous implementation of this idea is the random forest. Think of it as a team of trees, each giving its opinion, and final decision is made by the majority vote. Random forest works so well because they introduce randomness at two levels. One, each tree is trained on random subsets of the data. Two, each tree contains a random subset of features while splitting the data. This reduces overfitting where a model memorizes the training data instead of learning the general pattern. The result, a more robust and accurate prediction. The decision tree may be simple, but when combined into a random forest, they become incredibly powerful. Whether you are classifying fruit, predicting customer behavior, or even forecasting weather, this algorithm is a reminder that great things often come from teamwork. Another type of ensemble method is called boosting. While instead of running many decision trees in parallel, like a random forest, we train models in sequence, where each model focuses on fixing the error of the previous model. Combine a series of weak models in sequence, thus becoming a strong model. Because each sequential model tries to fix the error of the previous model, boosted trees often get to higher accuracies than random forest but are more prone to overfitting. Its sequential nature makes it slower to train than the random forest. Famous example of boosted trees are ADA boost, gradient boost, and the most common of all algorithms that is used for almost every algorithm exercise nowadays, that is XGBoost. What we have talked about so far is supervised learning, where we wanted to predict a specific target variable using some input variable. However, sometimes we don't have anything specific to predict, just want to find out some underlying structure in our data. That's where the unsupervised learning comes in, and we'll discuss that tomorrow.